Welcome again. As we started the teleoperation systems or derivation of the teleoperation systems or the introduction in the previous hour, I'll be going through the mathematical derivation in this class, in this time, and I'll show you how you can create teleoperation system or a bilateral control system with force transmission and position transmission between the master and slave sides. But before we move on, I would like to also make an announcement. I'll make this announcement available in the web also for the midterm exam. It's up to the professors to select the type of the midterm exam. And for our class, I thought it would be much more appropriate to make to give the midterm as a term project at the end of the term, at the end of the semester. We were anyhow planning to give a project. I just increased the percentage, the weight of the project to 40%, and that will act like a midterm. Probably in the last week of the semester, once we are completed with most of the derivations, you'll have your midterm exam. The project will probably contain certain derivations, simulations, results, and so on and so forth. So I'll make the announcement available in the web today in the Bilateral system, and we will have more time to discuss on this. So how can we create the controller? Let me write here how to create controller for teleoperation. So that's actually derivation of the bilateral controller. Okay, we will start with an assumption. Because what we want is to come up with a derivation that's valid for the easiest system. So we will be assuming two identical systems with inner loop disturbance observers and with reaction force observers. So what we want is to make the derivation for two copy-paste systems. Master and slave system have identical properties with inner loop disturbances and inner loop disturbance observers. That means that just coming up with the desired acceleration for the master and slave system to satisfy our goal would be sufficient for our derivation. So as always, don't forget, when we're trying to make a derivation for a control system, we first start by defining the errors. Let's start by defining the errors. These errors are simply ones that are there to satisfy these two goals. So in that sense, we can write here the error in position tracking, that's called EX, can be given as the master side position minus slave side position, where the error in force tracking EF can be given as the master side force response plus the slave side force response. So simply we gave these two objectives as the errors of the system, and of course our controller will at the end of the day try to move this error to zero value, either in finite time or in exponentially decaying way. And once we have the zero error for those two errors, we'll be satisfied with the goals of bilateral control system. So Without loss of generality, so let me write here without loss of generality. These two errors, the tracking errors, can be, I'm sorry, can be modified with the generalized errors as follows. So we can write here that position tracking is enforced by this error rather than the error given in the previous slide, that is x master dot minus x slave dot plus some coefficient alpha times x master minus x slave. So in other words, let me say this. Assume that we had only position control problem, and as if you're in the position control, you can write here it's the reference minus response, right? And remember that we were able to modify this with a more generalized error defined that way. So we were including the derivative of the error function itself with certain linear scales. I'll do the same for the force. EF can be modified with this one. Let me write here F master dot plus F slave dot plus beta times F master plus F slave. This beta is also a linear scale. Usually the coefficient of the function itself is bigger than the coefficient given, in the hidden coefficient given in the derivative side. So we can generalize these two errors that way. In order to provide you with a better option to trace these equations, I will call this equation 1a, equation 1b. Okay? And I will write here equation 2a, equation 2b. Because later on we'll have so many equations. In order to follow those equations in an easier way, we need these definitions. So the tracking errors given in equation 2, A or B, doesn't matter, can be forced to have zero value through a first order dynamics through the following equations. So remember why we moved to generalized error. That's simply with this one only applying first order derivative was sufficient, so that with an exponentially decaying behavior, transient, let me say, we were able to satisfy the two goals defined in the error functions. So ex dot plus, I can write here kx ex is equal to 0. That's the first equation, and ef dot plus kf ef is equal to 0. That's the second equation. So these two equations actually enforce the first order exponentially decaying error dynamics. So it means that no matter what initial value you have in the tracking error of the position or the force, they eventually move to 0 value after a while proportional to those constants, kx and kf. Let me write here, kx is greater than 0 and kf is greater than 0. You know that these are the coefficients of the decay rate of the error. I can write their equation 3/a, equation 3/b. Okay, so far so good. Remember what we were doing. We were basically taking this error and substituting to the error dynamics, trying to formulate a big algebraic equation from which we can extract the desired accelerations. And we're gonna stick up with the same methodology here because that's the same way of deriving the controllers. So substitute equation 2 to equation 3 gives the following. Well, what we have is that we have the definition of error in a generalized way. Just take this, differentiate, and take this, multiply by kx, and satisfy this equation. So substitute there in the equation. If you do so, you're gonna have those two equations: x master double dot minus x slave double dot plus alpha plus kx times x master dot minus x slave dot plus alpha times kx times x master minus x slave is all equals to 0. Well, you can write the same for f master double dot plus now f slave double dot plus beta plus k f force constant times f master dot plus f slave dot plus now beta times kf times f master plus f slave, all is equal to 0. So we have two equations. The first one is a nice equation, a good equation, because there you have the master and slave accelerations directly existing. So you can shuffle this equation. You can send this part of the equation to the right hand side and leave the accelerations alone. But in order to solve the system fully, you have to get rid of the second derivatives of those forces in the second equation. Let me go back and write here. Okay, these are equation 4/a, equation 4/b. Okay. Well, let me write. Now we can make the following trick. I hope you remember the previous week's derivation. In grasping control algorithm and in the derivation that's made 1 week before that in the force control application, we discussed that the environmental impedance is consisted of three main items. One is mass times the deflection's second derivative. The other is the damping ratio times the deflection's first derivative. And the third one is spring constant times the deflection itself. And we have come to the point where we told that the force generated by the spring side of the environment is, in most of the applications, dominating the mass induced force and the damping induced force. That's why in majority of the problems we can assume that a pure spring environment exists. So let me write here, we can assume that pure spring environment exists on the master and the slave side. Okay, so with this definition, one can write this. The master side force, the force encountered on the master side can be represented by certain stiffness coefficient K master times X master, and the slave side force F slave can be represented by K slave times X slave. Okay, so I think I can call these equation 5a equation 5/b, right? Now, replacing F master double dot and F slave double dot, remember that we had these in equation 4b, with K master, X master double dot and K slave, X slave double dot respectively. Well, in equation 4b, one can write down the following. So simply go back to the previous equation, equation 4b, just replace F master double dot by K master X master double dot and F slave double dot by K slave X slave double dot. Now you can ask a very, simple question that's naturally existing in your minds. Why didn't we change F master dot and F slave dot, or F master and F slave with these? Because in our system we are assuming that we have inner loop disturbance observers and reaction force observers, and we can, without loss of generality, we can assume that we are easily measuring the forces and the forces can be differentiated. This part is a little bit tricky. The differentiation of force is not always possible because force is usually a very noisy signal in motion control. But there are proper tools to differentiate the force and get the derivative of the force, which is called the Yang signal, to be used in the control loop. And I even wrote a paper on this, and there are several papers about that. So we can assume that the positions of master and slave system, the velocities of master and slave system, the force reactions, the reaction force on the master and slave systems, and the derivatives of those reaction forces are all being measured from the system. So we can extract these information. These are measured, these two. That is through differentiation. This is acquired by reaction force observers. That's a different kind of measurement or estimation. And these are acquired through proper differentiation. What we need is to replace F master double dot and F slave double dot with equivalent identities that has X master double dot and X slave double dot. So if we do so, we're going to have these two equations. Let me write the first equation, X master double dot minus X slave double dot. This is equation 4a actually replicated. I'll just send the remaining part to the right hand side. Okay, so we have, we have minus alpha plus kx, not s, kx times x master minus x slave, of course dot here, minus alpha times kx times x master minus x slave. This is the first equation. That's actually equation 4a modified now as equation, let me see, equation 6a. So the second equation is important. Go back. Instead of f master double dot, we're going to write here k master x master double dot. So km xm double dot. And remember, we were having the plus sign here for f slave double dot. And for f slave double dot, we are writing that ks xs double dot. That summation is equal to, similarly, minus beta plus k force kf times f master dot plus f slave dot minus beta kf f oops, f master plus f slave. So this is our equation 6/b. Okay, that's the sixth equation. Now, from this point on, the rest is simple algebra. It's not actually that simple. It's not that trivial, but it can be computed with the proper tools. You can hand compute it, but I already computed it for you. Now, let me go to the, well, I think I can write it here. I can change the color. Okay. Solving equation 6. When I say solving, actually I'm referring to that. Multiply the first equation by, let's say, ks. So you have ks xm double dot minus ks xs double dot, and add the second equation. So minus ks xs double dot plus ks xs double dot will cancel each other, and you'll have some coefficient multiplying xm double dot here being equal to something on the right hand side. So from this you can extract x master double dot. Similarly, if you change the signs and make a similar operation, you can acquire xs double dot. So that's what I refer to when I say solving equation 6. One can obtain the desired accelerations as follows. Well, that is x master double dot is equal to cmx. I'll call those coefficients coefficient of master in position control times e, well, okay, I can write it here, ex plus cmv times ev plus coefficient of master side in force times error in force plus coefficient of master side in yang, we call it yang, times ey. Yang is the derivative of force. I'll explain this in the next slide. Don't forget that this is desired acceleration. Similarly, the slave side desired acceleration can be given as c slave x ex plus c slave velocity ev plus c slave force times e force plus c coefficient of the slave system in yang times error in yang. Okay, I think these are last equations. Equation 7/a, equation 7/b. Okay, so if we move to the next slide, we can write those errors. Actually, when I wrote there ex, I was referring to x master minus x slave. When I wrote there ef, I was actually before this, let me write ev is x master dot minus x slave dot. the force error was F master, now with a plus sign, don't forget, F slave, because of the different signs in force tracking. And EY is the Yang signal, that is F master dot plus F slave dot. Okay, and the coefficients are, let me write the coefficients with a different color for you. Let me pick this one. Okay, CMX is minus alpha kx, let's write here kskx over km plus ks. These are actually computed in MATLAB environment, so I think they're correct. They shouldn't be wrong, but you can double check. I might also be having some errors. CMV is equal to minus alpha ks minus kskx over km plus ks. C master in force is equal to minus beta k force kf over km plus ks. Let's correct this. K master plus k slave, and C master in Yang is nothing but minus kf minus beta over k master plus k slave. These are master side coefficients, and I can write here similarly C slave in X is alpha km kx over k master plus k slave. C slave side velocity is alpha km plus km kx over km plus kx. C slave in force CSF is minus beta kf over km plus ks, and C slave in Young is minus kf minus beta over km plus ks. So these are simply the coefficients used, the coefficients derived after certain algebraic operations. What I want to do as the last thing in the presentation is to give you a rough sketch of the block diagram that makes teleoperation feasible. That's the block diagram of bilateral control algorithm that we just write. I will also provide you with certain videos, recorded videos, experimental videos, and with the block diagram of the simulation, or maybe with the code of the simulation, because in your projects I might ask from you to code all of these. So let me move to the next slide, and if I have time, yeah, I have a lot of time actually. So block diagram. What we have is this. Now I'm going to draw everything as sketches, because I think most of you are pretty much familiar with systems having the disturbance observer and so on and so forth. So I'm not going to explicitly show them in detail. I'll just write over there. Okay, this is master, this is slave, that is actually plant plus disturbance observer plus reaction force observer. This is also plant plus disturbance observer plus reaction force observer. So these plants can give us measurements in measurements in, let me write here, X master, right? So that one is X slave. We can write here X slave dot, and here X master dot. We can assume here that the master force comes F master. Similarly, the slave system force comes here F slave, and likewise we can assume that the derivative of the slave system force and the derivative of the master system force can be assumed to be measured from the system. Okay, so what we do is to create errors. Let's write it here. Here we have X master minus X slave, right? So let me erase this and this also. Let me try to express it this way. Perfect. So we have second signal somewhere here, plus, minus, and this is nothing but the derivatives. The third signal might be assumed to come somewhere here, right? And maybe, okay, these are with both positive signs, right? And let's also erase this part and this part. We can assume that we have the derivatives of the forces summed up there. This part is F slave, and this part is F slave dot. So we have those four signals. Actually, that is error in position, that is error in velocity, that one is error in force, and probably that one is error in yang, right? So this is position error, velocity error, force error, and the error in the derivatives of the forces. And don't forget that these two are defined as X master minus X slave, X master dot minus X slave dot, as what we have already written here. And the last two, EF and EY, are given through summations. So these signals are being multiplied by certain coefficients. So X master double dot is a linear combination of those error signals with the proper coefficients. So I think I can write here this. That input is X master double dot, and probably, well, this way. This way, I can also highlight it that way, and this way, and the last one is this one, right? So we have the extensions to the other side. Here and here, right? So coefficients for these. Now EX was being multiplied by C master X, right? CMX. And here C master velocity, C master force, C master Young. So these coefficients are already calculated. They're just scales and given in the previous slide. So what we can do is to put somewhere here a summation and make a summation for all of these signals. Similarly, we have here C slave in X as a scale, as a coefficient, C slave in velocity, C slave in force, that's the third coefficient we have, and finally C slave in Young, that's the fourth coefficient. So these four coefficients are also being summed up at the summation point to yield to our X slave double dot desired. Don't forget these are desired values. That's with a plus sign, another plus sign, and another plus sign, and finally we have another plus sign. So that is the block diagram of your controller. And if you'd like to be more precise, what we can call is that this part is our controller. So that red part is our controller. I'll not actually leave it on the slide because it doesn't look very good. I'll erase this, but before I erase, just remember that for the controller we're taking the errors, multiplying with the coefficients that we already derived in the previous slides. Let me erase this so that you don't have any problem. Okay, that's the block diagram of our controller. Okay, I think I'm at the end of my lecture. Please feel free to send me anytime email for any point that you didn't understand, because if you leave the things to the last minute, it will be really hard to catch up with all of those videos because you'll have lots of videos there. Try to study regularly, try to interact with me through mail. Some of you have already sent me certain mails. I'm trying to address whatever question you put out there first on the mail, and if we cannot come to conclusion, if we cannot come to an agreement, I'm usually trying to set a common appointment time for any one of you to describe in detail the point that you didn't understand. The reason why I didn't put an office hour is simple, because when I put this, I tried this in the past, and I always had objections from students claiming that they are not free at that time. They have either another class, or they are in the office hour in another professor, or they are making some projects, whatever. So it's really hard to find a common hour for every student. That's why, rather than this, I'm usually referring this right to be handled personally through appointment. So if you want to have face-to-face contact, and if you want to ask some questions, don't hesitate to write an email. Once again, I'm going to try to address your question in the mail, and if we cannot, if you still have further questions, we will be arranging a personal office hour meeting on a teleconference. Until then, take care, and don't go out, stay at home. See you guys.